All right, welcome everyone to our presentation for senior design. We're Team Spot, and our project is the acoustic source localization. So the goal of our project was to derive a direction of a single source compared to our microphone array. So our design approach was to use a 8-microphone array, specifically 7 microphones oriented in a circle and 1 microphone in the middle. This array is attached to a Raspberry Pi 3, and we implement a time difference of arrival with multilateration techniques for both near and far field localization. And here we have a video. All right, so in that last video, we got to see 2 examples of 2 single sources and how the angle changes on the GUI in real time. Our plot is oriented with a few angle values as well as the different ports that are on the Raspberry Pi to see where the direction of the source is. Also on our GUI, we have a few settings that we can change, like threshold, degrees of forgiveness, and brightness.
As for the algorithm behind this project, so for any localization problem, we will have 2 steps. The first step is called timing information acquisition, and the second step is using the timing information to convert it into distance information and use that to perform multilateration to locate the source. So for the first step, we will use generalized cross correlation with phase transform. The phase transform is basically a weighting factor that put before the ordinary cross correlation, has the effect of heightening the peak and lower the measurement error. And here we also briefly show the equivalent Python implementation that is using the FFT property of the cross correlation. And after that, we perform peak detection. The index that corresponds to the peak, after divided by the sampling rate and multiplied by the speed of propagation, which is 340 for sound, will get you the absolute distance period between 2 pairs of microphone and the source. So here we show some of the multilateration techniques we considered and implemented. The first one is called the linear least square. And here we show the masses. There are some advantages. The first one is it has a relatively lower complexity and also drilling estimating the X and Y. But the disadvantage is that it has a lower accuracy compared to the other linear approaches. Also, the estimator requires a matrix inversion, which might be ill-conditioned due to it being singular. The second method is called weighted linear least square. It has better accuracy because it takes into consideration a weighting factor that is in the form of the inverse of the cross-correlation matrix of the error matrix. The advantage is that it has better accuracy, but the disadvantage is that the matrix inversion has a higher complexity. The third method is called the constrained weighted linear least square, which is basically weighted linear least square with an additional linear constraint. The advantage is that it has an extremely good accuracy, but it has to solve a 5-root equation with some root finding algorithm. So it has a very high computational complexity, and therefore it's not supported by the Raspberry Pi with its very limited processing capability. And here we plotted out an error analysis of all the 3 estimators. As you can see, the constrained weighted linear least square approaches Cromwell lower bound. But because of its high complexity, we decided to implement linear least square in our Raspberry Pi. And here we have a far-field solution that is called averaging triangulation. So basically, for any given source, this algorithm will pick 4 pairs of receivers, microphones, and each pair will give you a triangulation that produces an angle that is between the source and the relative x coordinate. And after some outlier filtering and a variance filter and averaging algorithms, it will produce a weighted angle of angle of arrival that is between the source and the relative x-axis. And therefore, that angle can be plotted on GUI and update the LEDs. And in order to manipulate the operation range of our hardware, we also implemented thresholding. Basically, each channel related to each microphone has a different gain. Therefore, we statistically averaging all the gains to determine the average background noise, and then address the threshold based on that. And here are some of the references from IEEE papers.